Hello, my name is Sara Lopes, and today I will present to you a gene therapy with the potential to stop a devastating neurodegenerative disease. The disease is called Machado-Joseph disease, also known as Spinocerebellar Ataxia Type 3, or simply SCA3. Imagine receiving two pieces of news in the same week. The first, you are going to become a father. And the second, you have been diagnosed with SCA3. This disease typically starts around the age of 40, a time when many people have young children, active careers, and full family lives. But from that moment on, patients start to express some progressive loss of motor coordination and balance, and over the course of about 20 years or so, they gradually become completely dependent. And the impact is devastating, not only for the patients, but for the entire family. And today, there is still no treatment able to stop the disease progression. Although SCA3 is a rare genetic disorder, this is the most common form of autosomal dominantly inherited ataxia in the world, affecting approximately 110,000 people globally, many of them with children and having a 50% chance of passing this disease on to their children. Having no disease-modifying treatment for this condition, patients are condemned to mere symptomatic care, which represents a global burden of around 40 billion euros. This disease is caused by a mutation in one single gene called ataxin-3, which leads to the production of toxic messenger RNA and protein species that start to accumulate inside nucleus. And I often compare this to what happens in a city during a garbage collection strike. The waste starts to accumulate and everything goes chaotic. And this is exactly what happens inside neurons. These toxic species start to accumulate, disrupt neuronal function, and eventually lead to neuronal death. Several strategies have been developed in order to diminish the levels of these messenger RNA and protein species. Nonetheless, none of these strategies eliminates the genetic cause of the disease, but SilenSCAs does. This is a CRISPR-Cas9-based therapeutic strategy that has been modified in order to permanently suppress the mutant gene and, in this sense, inhibit the formation of toxic species at the source. In this mouse model of SCA3, SilenSCAs proved robust therapeutic effect, significantly diminishing the levels of the toxic protein aggregates and preventing the formation of characteristic neuropathological lesions. This technology is currently at TRL 3.4 and is being protected through an international patent application. All of these studies have been done using viral vectors, and this was good enough to make the proof of concept of SilenSCAs. Nonetheless, although effective, viral vectors can actually prolong the expression of this machinery and therefore increase the risk of unintended genome editing events. Therefore, our next goal is actually to develop a non-viral lipid nanoparticle-based strategy in order to allow a transient genome editing and, in this sense, accelerate a safer path towards clinical translation. Therefore, with this George Hoover's Award, we intend to develop some key de-risking activities, namely lipid nanoparticle formulation in vitro and in vivo validation to test the editing efficiency. And all of these studies will help us out generating a lot of data that will allow us to go to the next preclinical and regulatory milestones. Long-term run, we want to develop a dedicated spin-off in order to bring these SilenSCAs to patients. This project has been developed by a huge multidisciplinary team with vast experience in genome editing, gene delivery, translation research, and technology transfer. We work in the University of Coimbra, where we coordinate viral vector, national infrastructure for viral vector production. We have close collaborations with different pharmaceutical companies, clinicians, and patients. And importantly, in Portugal, and especially in the Azores, we have the highest prevalence of this disease, which gives us good access to these patients and a unique competitive advantage for translation. But at the end, this is not only about technology. This is about patients. This is about that same man that received two news in the same week, knowing that he's going to become a father while having a diagnosis for a disease with no cure. So our goal is that in the future, we can have a diagnosis that is not an inevitable sentence, but a disease that we can actually cure. And this is the future we are trying to build with SilenSCAs. Thank you.